Okay, in the last video we talked about the mechanism behind these radical substitution reactions. In this video we're going to talk about whether there's any specificity for which hydrogens on an alkane get substituted for, and what's the scientific basis for that selectivity. In this case, our example, in the last video, we're just substituting for a hydrogen on methane, and really all these hydrogens are the same, all four of them, so it doesn't matter which one we substitute for. But we might imagine there are some alkanes that have different types of hydrogens, and here's an example of T-butane. And if you look at this, you should ask yourself, well, how many different types of hydrogens are present in this molecule? And if you think about it for a second, maybe you should pause the video, but the answer is that there's really two different types of hydrogens here. There's this hydrogen, which is bound to a tertiary carbon, and then there are 9 hydrogens in a second group. All 9 of these hydrogens are equivalent to each other. They're all bound to a primary carbon, and they're all sort of bound to an identical type of primary carbon. And so when we think about maybe doing a radical substitution reaction on this type of alkane, a question could be which hydrogen is substituted for and why? Or is there any preference? So let's think about that for a little bit and think about really a propagation reaction that can occur on this type of molecule. Let's do this so I can write on the molecule. Let's see. Imagine introducing a chloride radical into our alkane. And really we've got two different possibilities that could occur, and I'm going to outline them in different colors. One is that the chloride propagates by stealing an electron from one of the carbon-hydrogen bonds on these terminal carbons. So we can imagine in blue sort of a new hydrochloric acid being generated, plus, if we use a skeleton structure here, a primary radical would be formed as the product. That's one possible avenue. Now the other possible avenue I'll outline in red is where a propagation reaction occurs where this chloride radical steals an electron from this carbon-hydrogen bond, the one in the other group. It again would form a hydrochloric acid. That product wouldn't be different. But the carbon radical that would form would be this one. We could think of this as a tertiary radical. Now, what do you think the selectivity is going to be for these types of propagation reactions? And why? Well, hopefully we've taught you enough about the different types of carbons that maybe your instinct might tell you that this tertiary radical is likely to be more stable than a primary radical. And if that's what you're thinking, you're right. For a lot of the same reasons that tertiary carbocations are more stable, we have this tertiary radical which is more desirable than a primary radical. And so if you were to choose which of these reaction pathways would be preferred or selected for, you might imagine that it would be this one to form the tertiary radical. And therefore, when this tertiary radical continued in a termination reaction, that we would see a preference for our tertiary alkyl halide as a product as opposed to an unstable primary radical terminating to form our primary alkyl halide product. So a reasonable prediction would be that this tertiary alkyl halide would be a major product and that the primary alkyl halide would be a minor product. Now that seems reasonable, and we can think maybe about describing why this would be a major product by thinking about a reaction diagram for really this part of the reaction, the formation of our alkane or alkyl radicals. So let's draw a graph here. Think about the x-axis is our reaction coordinate. And again, we're going to think about this for our propagation reaction, and free energy as the y-axis. We're going to have our chloride radical plus alkane, and we're going to form some sort of alkyl radicals as an intermediate in this reaction. Now, we've said that the tertiary radical is more stable than the primary radical, and so we can indicate that on our reaction diagram by putting our primary alkyl radical as having higher energy than our tertiary radical. And therefore, according to Hammond's postulate, the transition state leading to this more stable radical is likely to be more stable than the transition state leading to the less stable intermediate radical. Now, the net result of this would be that according to our reaction diagram, regardless sort of the relative energies of our products, is that the activation energy leading to the tertiary radical is lower, this sort of distance right here, than the activation energy leading to our primary radical. And so this reaction pathway would be faster. And so in a competition between these two different reaction pathways, the argument would be that since the intermediate of this reaction pathway is more stable in a rate-limiting step, the activation energy leading to that more stable intermediate is lower. Therefore, this reaction is just faster than that reaction. And therefore, we see more of its product than we do the slower reaction. It's just a matter of which one's faster. Okay. That all makes sense, and it's sort of satisfying if you followed the logic so far. But what if I told you that if you actually did this reaction, you end up with a slight preference for the primary product, the primary alkyl halide, as compared to the tertiary alkyl halide? That might be disturbing at face value. Based on what we have talked about so far in this video, that doesn't make any sense. Those experimental results don't match our theory. Our theory states this is the fast reaction due to the transition state being lower in energy to this lower energy intermediate as compared to the high energy intermediate in transition state. Now, if we think about it in a little more depth though, you might want to pause the video and just think about it. See if you can come up with an explanation for why these results happen. Now, if you didn't pause the video, shame on you. But we're going to talk about maybe a reason why we still see the major product being a primary alkyl halide. Now, what we've said about the speed of these two reactions is correct. Okay? But we have to remember how many hydrogens were in each of the groups. Our fast reaction can occur with one hydrogen. Our slow reaction has 9 possible hydrogens in which that can occur. Okay, so I like to think about this as a race around the track, perhaps. Okay, here's a track, the Agnes Scott track. Okay, and we have, let's say, one fast runner at the starting line here, and 9 slow runners at the starting line. Okay. Now, if we're sort of counting how many products are made from this foot race between a slow runner and a fast runner, let's say we make a tick every time someone crosses the starting line again as they make one complete lap. You might imagine at the beginning of the race, right, the fast runner just zips around really quick, and the first tick that we make is a red one for the fast race from the one hydrogen. Now maybe this is a super fast hydrogen and it actually goes around twice before any of the blue runners make it back to the starting/finish line. But eventually they do. Maybe they're a little less than twice as slow as the red line. Now all 9 of these slow runners come across and I start marking them down. Okay. In the meantime, another slow runner comes by, or another fast runner comes by a couple times, but then the slow ones make it through another round. And you can see why the major product in this case might actually be from the slower reaction. There are just more potential pathways to reach this product than there are to reach this product. Even though the pathway leading to the tertiary alkyl halide is faster, there are 9 different ways to make the primary. And even though it's slower, you get more of those products in the end.